All right, there's some molecules that actually don't have a chiral carbon, but it is a chiral compound. They're not very common, but we're going to see that they can be chiral because they have asymmetry, even though they don't have a chiral carbon. This occurs when you have bonds that can't rotate. Here, this is when you have two double bonds next to each other. It's called cumulated dienes. You can have a similar thing with two rings that are attached at one carbon. Those are called spiral compounds, and they can have the similar type asymmetry. The asymmetry comes because there's no symmetrical axis here. If I look at this compound and compare it to this, you can see that this compound has a hydrogen up and a chain that would be down. On this part of the compound, the chain is back and the hydrogen is forward. I'm going to hold this part the same and switch this side. If I do that, and I go and I try and superimpose it on top of this, you will see the R and the hydrogen cannot superimpose. So you actually get chirality here without a chiral carbon. Notice these carbons are all in double bonds, so they cannot be chiral if they're in a double bond. No big deal, just recognize that when you have compounds that have 3 dimensions like this and they're held so that bonds can't rotate, sometimes you can have some chirality result. And it has to be when there's cumulated double bonds or when there's a ring and a ring attached to the same carbon. They look like, when you see them, they look like, pinch your 2 fingers, a finger to a thumb and a finger to a thumb, and then put that pinch in the same place. And what you get are 2 rings attached at one point. That's when you can have the same kind of asymmetry that lends to a chiral compound without a chiral carbon. Now, there are some compounds that will have more than 1 chiral carbon. So you might have 2 chiral carbons. Each carbon has to be assigned a specific configuration, like we did with that molecule that had 2 chiral carbons. When we go to name them, we have to identify the chirality of each of those carbons. So what we do is we write the number, and then we follow with R and S, and then we write the number and follow with RS. And so you see number, letter in front of the name. Here's an example. This compound has 3 chiral carbons. So the number 2, 3, and 4 carbons are chiral. So we have to say 2R, 3S, 4S, or whatever it is that we figure out for that compound when we write it. And so each chiral atom is specifically identified. When you have a compound with 2 chiral carbons, you can find that there are 4 sets of possibilities. And what we're going to do is examine those 4 sets of possibilities. When I have 1 carbon, the R configuration is a mirror image of the S configuration. So they're enantiomers. But if there are 2 chiral carbons, there's 2 possibilities. I can have, on 1 compound, I could have R and R. Its enantiomer would be S and S. But there's 2 more possibilities. I could have R and S on 1 compound, and the other one could be S and R on the other compound. The 2 compounds that are RR and SS are enantiomers. And the 2 compounds that would be SR and RS are enantiomers, because the R and the S are exactly opposite on each carbon. So if I look at this, look down here at this compound, we have 2R, 3S. If I look at this, 2S, 3R, I know these are an enantiomer. If I look down here at 2s, 3s, I know 2r and 2r, 3r is an enantiomer of this. But what happens when I compare this compound, 2r, 3s, to 2s, 3s? What is that? When I compare two compounds and only one carbon is a mirror image and the other is not, like what I just showed you, they're not enantiomers. They're something called diastereomers. The definition of a diastereomer is actually a non-superimposable, non-mirror image of the same compound. So if I look at this, 2r, 3s is a diastereomer of 2s, 3s. There's another diastereomer of this. What do you think it might be? Think about it, and then we'll cover that. Okay, you should have said 2r and then 3r would be another diastereomer of this. So let's go ahead and look at two chiral carbons in a molecule that has a plane of symmetry. If I have a compound, let's look down here at this one. It has two chiral carbons, 4 different groups on each carbon. So this is a chiral carbon and this is a chiral carbon. However, if I go and assign chirality, none is shown here, but let's say I assign chirality and I find this side is R and this side is S. The R is a mirror image of the S. This gives that molecule a plane of symmetry, and that plane of symmetry makes it a chiral. So even though you would have individually chiral atoms, the molecule as a whole is a chiral. What we're going to do is we're going to look at a similar compound to this one, and we're going to go through all the possibilities and try to examine how each of these possibilities are related and how, when this arises, we find that it is a chiral. This compound to this compound. This is S and S, and this is S and R. I know that this compound is not a mirror image of this one. How do I know that? Well, I know this compound is a mirror image of this one because S and S are the opposite of R and R. So this and this must be mirror images. But if I go and compare this compound to this one, the S and the S are the same, but the S and the R are mirror images. So if I go and I try to put this molecule inside of this one, you would find one side fits perfectly, the S fits with the S, but the S and the R are going to be non-superimposable. So what we find is that these two are not mirror images and they're non-superimposable. That makes them diastereomers. There's another set of diastereomers here. If you look, you can find it. If I see R and S and compare it to R and R, what I find is R is the same, but R and S are different. They're mirror images. So one part of the molecule is a mirror image and the other one is superimposable. Mirror image, non-superimposable, this one superimposable. So altogether, RS is a non-superimposable and non-mirror image of RR. So we call those two diastereomers. If I look at this one, SSRR, those two are mirror images and they are non-superimposable, so we call them enantiomers. However, if I compare these two over here, what I find is these two, the R and the S would be a mirror image, and the S and the R are a mirror image. And so this compound is a mirror image of this compound, but they are superimposable. So because they are superimposable mirror images, they are the same compound, not enantiomers. This only occurs when this side is exactly the same as this side, and that the R and the S are opposite. You can flip the molecule over, and because the groups are all the same on each carbon, R and S is the same thing as S and R. We call these two compounds together a mesocompound. There is a plane of symmetry here. The R is a reflection of the S. This plane of symmetry is what takes away the chirality. You can take this molecule, turn it over, flip it, and put the S up, and it becomes this molecule. These two structures, they're the same compound. We call them a mesocompound. Mesocompounds have chiral carbons, but they have a plane of symmetry that makes them achiral. How do you tell? You can actually tell just by looking at the names. If I look at enantiomers, they are always going to have exactly the opposite chirality on the numbered carbons. For diastereomers, what you have is that one is switched and the other is not. One is switched and the other is not. However, if I go and compare this to this, they look like they'd be enantiomers. If the groups on the on the 2 are the same as the group on the R, then they are a mesocompound. If they have different groups on the S and the R, they can't be mesocompounds. There has to be that plane of symmetry. So you must look and make sure that the groups on each carbon are the same. And then the S is a mirror image of the R, and it's a mesocompound. The physical and chemical characteristic of enantiomers, whether there's 2 or 3 or 4 carbons, regardless, they're going to be chemically the same when reacted with chemical substances, but chemically different when you react with chiral substances. The physical characteristics are going to be exactly the same otherwise, except for the rotation of light. That's always, of course, exactly the same magnitude but opposite direction. I hope you can't hear that drill. Okay, then if I look at diastereomers, when I compare one diastereomer to the other, what I find is they are chemically different, whether they're reacting with chiral or achiral substances, and the physical characteristics are different. For instance, one diastereomer might have a melting point of 200 and the other one 300. The boiling points are going to be completely different, and the solubility is going to be different. So you can actually, they're very easy to separate because their physical characteristics are different. However, enantiomers, they're very hard to separate. If I have a mixture, a 50-50 mixture of enantiomers, for instance, R bromobutane, 2-bromobutane, and S2-bromobutane, there's no rotation of light because R will rotate it one way in a particular magnitude, and the S will rotate it the opposite way in exactly the same magnitude. So you would find that the mixture did not rotate light. However, you can have 40-60 mixtures and there will be a net rotation of light. The compounds are still chiral, it's just you can't detect it because the S rotation cancels the R rotation. The mixture 50-50 of 2 enantiomers is called a racemate or a racemic mixture. The chemical characteristics are going to be the same as for an enantiomer. You're going to have all the melting points, boiling points, etc., are going to be the same for the racemate as for the enantiomer. It is just going to be that you don't have rotation of light. Okay, now on these compounds, I want you to determine which of the following compounds is chiral, which ones have a chiral carbon. So I've drawn the structures for those compounds you don't know how to name. You do know how to name methyl cyclohexane. So go ahead and look at these compounds and determine which ones have a chiral compound, a chiral carbon. Okay, there's only one compound here that has a chiral carbon, and that's 2-bromobutane. If I look at 2-methyl 2-pentanol, you can see there's 2 methyl groups on it, on this carbon, and so that carbon is not chiral. The rest of these carbons all have more than one hydrogen, so they are not chiral. So the entire compound is not chiral. If I look at this compound, I can see there's a methyl, an ethyl, a hydrogen, and a bromine. So this carbon is chiral, and the molecule is chiral. Methyl cyclohexane has symmetry because one side of the cyclohexane ring is the same as the other side of the cyclohexane ring, and so this is not chiral. 2-propanol has a methyl group and a methyl group and a hydrogen. The methyls are the same, so it's not a chiral compound. Which of the following molecules below is optically active? Okay, so if I look at these compounds, optically active means has a chiral carbon in it and no symmetry. So if I go and I look, this molecule has a methyl group with 3 hydrogens, a carbon in a double bond, a carbon in a double bond, and a methyl group that has 3 hydrogens. None of these carbons are chiral. If I look at this molecule, cyclohexanol, it's like methyl cyclohexane. There's a plane of symmetry right through this molecule because this side of the molecule is the same as this side of the molecule. If I look at this molecule, you can see there is a carbon that has a chlorine, a hydrogen, a methyl, and an ethyl. So this will be optically active. What are the chirality centers in the molecule shown below? Okay, a chirality center is basically a chiral carbon. So if I look down here, I will find that this carbon has 1, a hydrogen, 2, a hydroxyl group, 3, a methyl group, and then 4, this long chain, 4 different groups. So this is a chiral carbon or a chirality center. This carbon has this group, which is different from this group, which is different from the hydroxyl group, which is different from the hydrogen. 4 different groups, so this is a chiral carbon right here. This carbon has a hydroxyl group and this group, but there are 2 hydrogens, so it's not chiral. So this carbon and that one are chiral and none other. What are the chirality centers in this molecule? So if I look at this molecule, I'll see a chlorine, a methyl, this carbon chain, and a hydrogen. So this is a chiral carbon. If I look at this carbon, this carbon, this carbon, and this carbon, there are more, and this one too, and this one too, there are more than 1 hydrogen, so they can't be chiral. You might have looked at this carbon and said, this group is different from this group, but it's not. This is an ethyl group, and this is an ethyl group. So this carbon has 2 groups that are the same. It is not chiral. What is the absolute configuration of this molecule? So if I look at this molecule, I'll see the hydrogen is already to the back, and it's the lowest priority group. So now I just need to assign priorities to the rest of these molecules. This is highest priority because the oxygen is greater than the carbon and the carbon. The ethyl is higher priority than the methyl because the carbon here outweighs a hydrogen here. So what is the, is it counterclockwise or clockwise in the rotation? If I look, it goes 1, 2, 3. That is counterclockwise, so this is S. What is the absolute configuration of this molecule? If I look at this molecule, you might have thought that it's not a chiral compound. But you have to see, there's a hydrogen, a hydroxyl group. This side is different from this side, so this carbon is chiral. Now we assign priorities. The hydrogen is to the front and it's the lowest priority. We'll take that into consideration, that it's coming to the front after we assign rotation to the rest of these groups. 1 is the priority up here, 2 is the priority here, and 3 is the priority here. So if the hydrogen were to the back, this would have clockwise rotation. But because the hydrogen is to the front, it has counterclockwise rotation. So it is S. Okay, go ahead and assign priorities using the Kahn-Ingold-Prelog rules that we've been using all along. To do this, we look at the first atom. They're all the same in each group, carbon, 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 carbon. Then we look at the next atoms, carbon, carbon, hydrogen, oxygen, oxygen, hydrogen, carbon, hydrogen, hydrogen, and fluorine, hydrogen, hydrogen. Which one of these? Well, oxygen outweighs carbon, so oxygen is higher priority than these two groups, but fluorine outweighs oxygen, so the highest priority. Okay, so which of the following compounds is chiral? Go ahead and pause the lecture and figure that out. Okay, so if I look at the top molecule, you can see this side of the molecule is the same as this side of the molecule, so this carbon is not chiral. So this compound is not chiral. If I look down here, you're going to see the same thing. This side of the molecule is not is the same as this side of the molecule. So both cyclohexanol and 1-methylcyclohexanol have the two sides of the carbon having the same groups on it. If I look at this molecule, it actually looks like you might have a chiral carbon here because that's up and that's down. But look, this side of the molecule is the same as this side of the molecule. So this carbon and this carbon are not chiral. However, if I look at this molecule, I'll see that this carbon has a hydrogen, a methyl, and that this side of the ring is different from this side of the ring. Likewise, on this carbon, you have an alcohol group, a hydrogen, and this side of the molecule is different from this side of the molecule. So there are two carbons that are chiral, and that molecule is the chiral molecule. Which one of the following is achiral? Now, in order to draw these molecules, we haven't really learned how to do nomenclature of these molecules. To do nomenclature of these molecules, you realize that on the number 2 carbon of pentane, you have a chloro group. On the number 3 carbon of pentane, you have a chloro group. On this pentane, on the 1 and 2 carbon, you have a chloro group. And on this compound, the 1 and 3 carbon have a chloro group. Go ahead and draw these out and see which one is achiral. Okay, if I draw these out, I would find that on 2-chloropentane, you're going to have a chiral carbon because there would be on the second carbon a chlorine, a hydrogen, a methyl group, and then you would have a 3-carbon chain or a propyl group. If I look at 1,2-dichloropentane, you would have on the number 2 carbon, the number 1 carbon would have 2 hydrogens on it, so it would not be chiral. The number 2 carbon has a chlorine, a methyl group with a chlorine on it, and then you have a 3-carbon chain on the other side and a hydrogen. So this would have 4 different groups on the number 2 carbon. If I look at 1,3-dichloropentane, the number 3 carbon would have a chlorine, an ethyl group that has a chlorine on the number 1 carbon, and then an ethyl group that has no chlorine on it. So this has 4 different groups. The hydrogen is the 4th. And so is chiral. However, if I look at 3-chloropentane, you would find the number 3 carbon has a chlorine, a hydrogen, and then an ethyl group on one side and an ethyl group on the other side. So that compound is achiral.